So today I want to do something new. I want to put what is invariant in a more familiar context of classical algebra and topology. Also define the other candidate for twisted Alexander polynomial. As I said, what is invariant is most of the time what people mean by twisted Alexander polynomial. But there's another one that's competing and has its advantages. They're very closely related. So, warning. Well, actually, before the warning and reference, a lot of the notation that I'm using is adopted from twisted Alexander invariance, Weidmeister Jordan, Cassie-Gordon invariance. Oh yeah, Kirby-Livingston. And this paper, which appeared in Topology, volume 38, what year was this? 1999. Is really the first paper that tried to put this stuff in a more familiar framework. It took a lot of the combinatorial ideas that have been floating around by many authors, like Wada and Cha and so on, and kind of re-examined them. It's quite a useful paper. There's also a paper that Susan and I have on archive called Dynamics of Twisted Alexander Invariance that does this, uses much of the same notation and takes a different point of view. So the warning, what's the warning? The warning is there's a lot of notation. Unfortunately, we've seen a lot of it already. So you'll see that we're very masterfully working our way up to this high level of notation. So let's go ahead with the notation. Some of it will be very, very familiar. If I write pi, I need the group of a, it can be a link today, group of a link. And if I write this sort of thing, I'm referring to the verting presentation from the diagram. So the link has components. I say D components. X0 will always mean a meridian of the first component of the link. So if you don't have it not, then you have to choose a component for the deal.
You want the relations to be one less, even if...
Yes.
Yeah.
There's always one redundant, so we just throw it away. And epsilon, as we said before, the augmentation map, which goes from pi to z to the d, thought of as a multiplicative group. So a group of monomials, if you will. So this is T1 over TD, and TI, TJ, TJ, TI, for all I and j. That's how we're going to think about z to the d. Here's a nice notation. Very likely Susan will be using it. If I write t to a vector of integers, I'll denote a vector of integers by n with a lower line under it. What I mean by this is t1 to the n1 up to td to the n sub d, where n is the vector of. So actually what this does is it allows you to think about z to the d as a multiplicative group. But if you wish to think about it as an additive group, this is how we need to make the translation. This is very handy notation. I think this actually comes from dynamics. That's very, yeah, it's very nice. So here's gamma, always representation from pi to g ln r, where r is the theorem of d. And we'll usually use the notation of little xi goes to capital Xi will be the matrix. Well, so far it's all familiar. Let's let V be R to the n. This is a free R module of rank big N. And pi acts on this. So this is a right Noetherian Z prime module. By Z pi, I mean pi acts on it. You can look at the group ring, formal Z linear combination of elements of pi. That's a ring. And then acts on R to the n. And how does it work? If I take a vector V, V will always be a vector in capital Z. And I take an element of pi. It's quite simple what we do. We take V, and then we take the matrix that the representation sends G to. And that's an n by n matrix with coefficients of R. So we'll get a new vector. And that's the action. And then, of course, you extend. You extend this linearly over the group ring. Okay, so another bit of notation that we've seen already. R. Well, I'm going to write Z to the D. What that means, remember, we're thinking about Z to the D as monomials. It's a group ring over the free group of monomials. This is just another way of saying polynomials in the variables. It's just a little more compact notation. And if you think this is not compact enough, then we'll simply write this as lambda. We've been doing that already. So now, what we want to do is we want to take V, and we want to take lambda, and we want to multiply elements of V by polynomials. And you just think about this formally as a polynomial multiplied by a vector, but to do it rigorously, you take a tensor product. And what do they have in common? Well, the scalars. So, if you're not familiar with this kind of a thing, it's nothing to be terribly concerned with. You just allow yourself to imagine a polynomial multiplied by vector formally as a scalar. Think of these as blurry scalars. You know, you're extending the scalars.
I mean, in some sense, it's lambda to the n.
Lambda's what?
It's lambda to the n.
Yeah,
because
exactly.
V is
of course
free.
it is. Of course, yeah. It's lambda to the n. So this is a right pi module. Basis. I haven't said it up here, but I should say, here we have a basis. E1 through En always. We use that notation. So here we have a basis 1 tensor E1, 1 tensor En. Because I can multiply by any polynomial and put anything I want here. And then I can add these things together and get anything I want. So there's our basis. And
are you using just the action of V, or are you
yeah,
using the action of...
so I'll explain it now. So what's the action? P tensor V. So this is a general non-polynomial. This is a general vector. How does G act? Well, G comes over here and multiplies by T to the augmentation of G. So this is some monomial in T1 through Tn. This is a monomial in T1 through Tn. And you multiply P by that. And then what about G? What about V rather? It's a V times gamma of G. It's just this action. So that's I'll box it so that I won't erase it because I'll use it.
Time.
Yeah.
Time. Or just change the value.
Here? Here?
Next slide. Another slide.
Here.
Yeah.
Oh, that's just multiplication. Yeah. That's just polynomial multiplied by polynomial. Polynomial multiplied by monomial. All right, so other notation, as before, X is the exterior of L. we've used x prime to be the universal revealing cover so that we can reserve for today x tilde, the universal cover. As I said before, one way to remember x prime is the universal abelian cover is to remember that pi prime is the usual notation for the commutator subgroup. So x prime is the cover that has fundamental group pi prime. So we consider the universal cover, and we look at all the chains, cellular chains on that cover. With coefficients R. And this is a free R pi module with a basis over R pi that you get by taking each cell down in X and choosing your favorite lift and fixing it. You only need one lift, because you'll be able to use pi to move you all the way around. So, basis obtained by choosing a single lift of each cell of X. So, I'll say a bit more in a moment, but for convenience, we can always collapse X. X is our link complement, and it has non-trivial toral boundary, tori boundary. We can always collapse X to a two-dimensional complex. And in some situations, it's going to be important that we do this by simple homotopy equivalence. But for purposes of computing first homology, twisted homology, we're going to be doing, actually it can be more brutal than this. If you're only working with H1, you can in fact, just homotope it any way you like. You have to be a little bit careful then if you're going to start looking at issues of H2. So let me just say right now we'll just be collapsing. But once you do this, you can get a single zero cell, which we'll call star. Think of it as a base point on another group. And we have cells, one cells, and we have two cells. Oops. Which we think of as our relators. And now we have to lift. We have to pick a favorite lift. And this is a little bit, maybe it's a dangerous abuse, but I'd rather do this. I'd rather use the same letter for the designated lift. It's only going to cause a problem once, but be careful. Avoid writing tildes and falling down. So they're not designated lifts. Same symbols. I'll do some very specific and simple examples.
So lifts in X.
Yes, thank you. Lifts in. That's right. In X. And the late, so that's right. So this becomes a single zero cell. This becomes specified one cells, and these become specified two cells.
Do you need your lifts to?
Nothing.
Do you just want to make sure that they're overlapping the same when you?
Nope. Just pick one. They can be very strange. There's no reason. I mean, you can pick them any way you want. It won't change anything.
And it's a different choice. And 2n plus 2. I mean, you're not making one choice, and that's sort of determining the rest of them.
I'm lifting say x0 to one particular cell in the universal cover.
Right.
But remember that I'm thinking about the cells in the universal cover as our pi module, in particular pi axon. And so pi will move that cell to any other lift of that cell that I wish. So if I want to think about this as our pi module, then I really only want to pick one lift and fix it. It's like a vector space basis.
Right, but you're picking one lift for each of the
Yes,
cells.
for each of these. Absolutely.
You have 2n plus 2 choices.
Correct. That's right. That's right. The two n plus 2. Yeah. That's right.
And not like the choice of the one cells is determining. I mean,
He's not worried that the boundary of the two cell is his one
Okay.
cell.
No. It'll come into the boundary maps. No. It'll
Very even then. But suppose you wanted to make it all connected.
What if you want to make it more efficient?
So visually,
If you want to pick
You want to make it
one
visually
cell
nice.
starting with the
Yeah,
base.
I would start them all. I would do it in this order. I would pick the lift of start, and then I'd pick lifts starting at my lift of start, and then I'd pick lifts here
But-
starting. Yes,
but
but
that's
you don't
not
have
necessary.
to. No, it's not. I'm not sure why you don't want to do that, but making so.
How do you see adjuncts to these two components?
Well, you gotta think in the case of a non-complement. You can think about you've got a zero cell and one cells and two cells and a free cell. But because this manifold has boundary, you can push on a face of the free cell and push it in. And that's what I mean by collapse. You can collapse this whole down to sort of a canonical two-dimensional complex. It's just convenient to think about it that way. Remember, in the back of your mind, you should be thinking about Wada's result that says that the Wada invariant is really a group invariant. So basically, we're looking at the complex, the sort of the canonical complex associated to a representation. And I'm starting by vertical presentation, so I'm using a very special kind of complex, and again, just pushing on those three cells. But if you wanted to use any presentation of a group, as long as you're content with H1, the first homology, you're not going to start messing with H2, you're going to be fine. Right, so that's keep going. Right. Yeah.
is there a nice two complex that collapse into for vertical?
For Vertinger? Yes. Oh yeah, yeah. You get this nice standard Vertinger relations. Yeah.
Take a vertical arc and cross.
Yep. Yeah. Works very well. So okay, so we're almost there. I want to use this symbol because I don't want to write too much. Will mean the complex, the chain complex that we get in this way. We've got our cells up here. I'm going to, excuse me. This will be a shorthand for this. I'm not nuts about this notation, but at the end of the talk, we'll see a nice way to shorten it a little bit in a way that's suggestive of some results. Well, what does this mean? Lambda, tensor V. Tensor are chains on the universal cover. And this is over our poly. So, what do you think of these? These are your chains in the universal cover, and these are your coefficients. Think about the coefficients of your chains being polynomials multiplied by vectors. It's a lot of information. And once you, and I'll show you what the boundary map is. It's essentially this boundary map. I'll show you the boundary map by an example. The boundary map is very natural, but the point is that we're going to get these chain groups and homology groups. These are going to be are finitely generated. lambda modules. Lambda modules. I just want to think about them as lambda modules. And what's the action? If they're a lambda module, I have to tell you how monomials act on these chains. So if I take a typical chain, I can let this be anything. Let's call it 1. Then V tensor Z. This is simply t to the n tensor V tensor Z. In a sense, this is shifting you. This is shifting you in this monomial direction. Yeah. Well, that's the end of the notation. Now let's do a simple example where I think you're going to see that things are pretty natural.
What's Z?
Yes?
Parameter chain complex.
Is V tensor?
That's a tensor.
Oh.
Yeah.
1 tensor V is a coefficient.
One tensor V. Yeah, I mean, we can put parentheses around it, to kind of suggest we have this. But I've dropped the parentheses, so you're right to squint at that. Technically, I suppose there are parentheses here. But tensor products is associated. Okay. So, eager to show you a simple example so that you really see what's going on and you actually see how to compute all this stuff. Yes?
It's tilde or just X?
X tilde. Oh, good question. Good question. No, it's denoted with X. And this information is telling us the process we went through. This is, you can think of this as the homology of X twisted in this way. Of X twisted in this way. And by the way, things like this are done commonly. Before twisting was introduced. This is not an unusual way to think about homology. Say if you want homology of equivalency of the cover, of looking at the chains of the universal cover, and then forming a complex V tensor by lambda. If I just get rid of V, then V tensor, the chains on the universal cover, are actually a way of describing the homology of the infinite sigma cover, or the universal field cover. This is commonly done. So the new ingredient here is V. So here's an example that we're looking at already. So pi is trefoil group x0 and x1 and x2. But you can actually use one of the relations that collapse x2 down to a combination of x0 and x1. So let's write it like this. And if you do it, actually, you'll get the very familiar relation. It's the usual way that the group of the trefoil is written. Now, the zeros and the ones get to be a little cumbersome. So when we're in a situation where we just have two meridians, x0 and x1, we're going to call them x and y. We'll make our life a lot easier. Okay? Just remember that they were verbal generators. And the picture. This picture. Here's x. And here's y. Okay, so what do we get in this case? Well, we have two chains. We have one chain, and we have 0 chains. And for a basis for the 0 chains, all we need are 1 tensor V tensor the base point, where V is chosen from E1 through En. In other words, we have capital N chains to generate. Okay. Remember, V is a free, capital N, free is a R to the capital, free R module break in. Now, for the 1 chains, we have a similar thing. We have 1 tensor V tensor X. Again, V is chosen from here. We also have one tensor v, tensor y. And for the relation for the two chains, we have one tensor v, tensor r. Now, what's r? You can think of r as a difference of two chains, where you could write it as a single chain, write it as a vector, really easy way. So, let me tell you what the boundary map is on del 1. So in this theory, the boundary map is simply, you take a boundary of a chain by applying it here. And then when you take the boundary, you get coefficients on the chains of one dimension lower, which you can then pull back. That's the gain. So the boundary operator is defined by a simple boundary operator on the chains of the universal common. So here's how it works. This is definition. One tensor v tensor x. Now, with x, down in the knot complement, that's not correct. Down in the knot complement, x is a loop. This is a star. Down in the knot complement, there's x. But up in the universal cover, we start at our designated lift, and we start traveling along. We don't wind up back here. Where do we wind up? We wind up at this base point, acted on by x. Right? So we wind up in, I guess we've been writing our action on this side. So the element is an element of the fundamental group, and it translates the base point to that point up in the universal column. What that means for us is that this boundary here is star x, x acting on star minus star. Think of that as the group translating this zero cell, fixed choice zero cell. And let's break it up. And now, remember that we've got this tensor product. So we can bring that element little x over here. We can bring it over here and act on this. How does it act here? Well, here's the way it acts. So now when I bring this x over, it's going to go here. And it's going to act on this by the augmentation of x, which in this case is just 1, so this is going to become t. And it's going to act here. And it's going to be v acted on by the matrix x. So if you get this, you get like 90% of what you have to get for working with these things. Okay. So let me just spell it out. 1 tensor v acting on x. I won't do them all in such detail, but if we do this one very carefully, then I think we'll see the key. And now we use that to write this as, let's go up here so you can see it. This gets that as t to the epsilon x, which is t. And so we just get t. I'm only writing t because there's only t1. And then star v, and this is the matrix x. And the base point, and we have minus tensor v tensor base point. And let's go one step further with this. Remember that we've got this action of lambda on here. That this thing, by definition, is 1. Tensor star tensor base point. This is how the action goes on this thing. It just operates here. It just shifts this over. Well, if I wanted to start to make a matrix for delta 1, if I wanted to write down the matrix for this boundary map, what would I have? I would be recording up here these things. And so what I'd have here would be really, think about it as E1, E1 tensor star, En tensor star. Where are these things? Well, I don't need to consider those if I'm going to view this as a lambda homomorphism. So I've got lambdas, I've got t's that will appear in the matrix. So the only things I have to really worry about are the E1 contribution, the En contributions, and I'll let the scalars in here take care of things like that. And what goes in here, what goes in the first block, is Tx minus the identity. That's coming from this first, that's coming from here. It's the image of this. I'll explain more in a second. And what's going in here is Ty minus the identity. Why is that? Well, because you can see here that we need Vx. We need x acting on V. Because V is on the left of the matrix, if I put E1 here, this is the first row of x. If I put E1 here, then I'm getting the first row of x, which is giving me the contributions from E1 to En of, I'm not sure how to say this, but let's just look at it quietly and see that this is correct. That's one of the reasons why we're multiplying on the side. I mean, this is EI times x is the ith row of x.
Is x a capital N by N matrix?
X is capital N by N, absolutely. X is N by, remember, x is in GL.
So
Okay.
2n.
Sorry?
This is a 2n by.
So yeah, this is not a square matrix. This is not a square matrix. This is we have n rows here, and here we have 2n. Yeah. Okay. Well, the calculation for del 2 is extremely similar. And we can use a little trick that I mentioned yesterday. That is, we don't have to write this as a relator. We could. If we want to think of this rigorously as a lift of a cell, we should probably be writing R as a relator. We can write it as a relation over there because of the box calculus. So I'm going to write this as 1 tensor B tensor. I'm going to think about this as a difference of two chains. And now we have to work through this thing. So this is 1 tensor B tensor del 2 x1 x1. Like I said, if you don't like this, use xy inverse x inverse y inverse, and you didn't get the same thing. So to work a little harder. Okay, so this is the one place, folks, where maybe we like to have tildes on our lifts, but as long as we keep our heads about us, we save a lot of writing later. So I'm going to lift this first I lift x, starting at the base point x in the universal cover. And so we just call that the cell x. And then I have to lift the next cell, but this one starts at x times the base point. Because once I lift x, I'm now at x times the base point. And that's where I have to start lifting y. So when I lift this one cell, I'm not getting y, I'm getting x acting on y. You know, this is where maybe it'd be nice to have those over there so you don't get confused. Okay, and then over here, at this point, once I've lifted these two, now I'm at the base point xy star. xy star. And now I have to lift x. So I don't get x, but I get xy acting on x. This is Fox calculus. This is the whole idea of Fox calculus. So
That lift of y is the one called xy. So are you actually assuming that your designated lift y
Yeah.
starts at the same base?
yeah, you're right.
I was wondering if you were saying anything at the time. That
Yeah,
you
you know.
started.
Yes, you're right. I wasn't thinking that far ahead. There is a good reason then to pick your lists wisely. We'd be working harder now. I think I did say something like, I don't know why you do it. You might have to work. You might have to do something
I
later.
think you really do want those lists.
Thanks for pointing that out. Yeah, we really do. Okay. And again, let's just be brave here and write it this way. Okay, now we subtract the lift of this cell. And like I said, if you used xy inverse, x inverse, y inverse, the Fox calculus would be giving us the same thing. So just all the relations in our group will be giving us the same answer. We're going to get this way is much simpler. Okay, so now when I subtract this one, I get y. Lifting this, I get y. Then I get y acting on x. Then I get yx acting on y. Now, all of these things, this one, this one, this one, and this one, once we break this up as 6 chains, we can then bring those over in exactly the same way we did it over here. So, what do we get? Let's skip a step. This one is just 1 tensor v tensor x. Let's see if we can do this okay. This one here, the x will come over, make this a t. It'll make the v vx. And then it will be by itself as well. This one? Well, what's the xy going to come over as? The t squared. Yeah, because the augmentation of xy is t times t. They're both meridians. So we get t squared, right, t squared. And then what's this going to be? Capital XY, exactly. And then it's tensor x, because x is the designated term. That's how this works. Over here, I get minus 1 tensor v tensor y. And over here, I get minus, don't worry about the minus signs, just carry them along. This becomes a t, just as before. The y tensor x, and then minus t squared v yx tensor y. When we finally get our matrix, you're going to see that there's a very familiar thing coming out of this. Okay, so this is 1 tensor v tensor x. Let's collect that one. Let's take this one, bring it next, but let's write it as t squared 1 tensor vxy tensor x, using the fact that this can come out. Let's take this one, putting all the x chains together, and this is t times 1 tensor vy tensor x. And then we do a similar thing with the y chains. So with the y chains, we have, let's write this one. Just which one we write? T times 1 tensor dx tensor y. That takes care of that one. Minus 1 tensor v tensor y. That takes care of that one. Minus t squared 1 tensor v x tensor y. So now, if we wanted to write the matrix for del 2, you see something very nice comes out of this. We're going to need now a column for the x chains. And so this is going to look like E1 tensor x, En tensor x. We're going to need columns for the y chains. We're going to have only one relation. But the relation goes in here is identity, let's see, plus t squared xy minus 2y. Now, for y chains, it's going to be t x minus identity is t squared yx. And these are n by n matrices. Now, just have to think about that for a little bit. Think about what happens on E1, E2, and so on, to see that this is correct. But this is just the Fox partials that we're getting here. This is nothing more than the partial arm with respect to x evaluated at big phi. Remember, big phi is the big representation that takes little x to t times the matrix x. We used it last time. And the other column is that. So the Fox derivatives give us these second boundary maps. You don't really have to do what we just did. That's the answer. We don't. This is going to be a general thing. You can immediately get something out of this. If we look at the first boundary operator applied to T inverse tensor V tensor y minus x, and you just follow through what we did. Just look at the calculations, and what you'll get. I believe this is sort of an exercise to check this. That this is one tensor. It's one because I started with T inverse. So things cancel out, and you get V y minus x tensor star. Now, if x is a 2 by 2 matrix, parabolic matrix 1, 1, 0, 1, and y is the matrix 1, 0, w, where w is an algebraic unit. So I'm working over the complex numbers. So these are yes, they're in SL to the C. Then, if you compute the matrix y minus x, this is 0, minus 1, w 0. Remember, this w showed up when Susan talked about Riley polynomials and the parabolic representations you get for two bridge numbers. In fact, every non-abelian parabolic representation, take two meridians that don't commute, and up to conjugation, you can assume, Riley proved this, you can assume that x goes, one of the meridians goes to this matrix, and one of the meridians goes to this matrix. And if W is an algebraic unit, then this difference is unimodular. The determinant is a unimodular. Unimodular means that this is surjective. And so therefore, delta 1 is onto, and therefore the zeroth homology vanishes. So, so this is this is true whenever you have non-abelian representation, non-abelian parabolic representation with the unit operator. So it happens very naturally for two Richmond's. It also happens with the total rep that Susan was talking about. True. Also, for the same reason, for total reps, which will probably come up again if you don't remember what they are. So, one more thing. I think I'm going to skip the proof of this. It's very, well, actually, it's kind of a nice proof. Let me go. Let me try. Start a little bit, but I think this is such an important result, especially considering some of the examples that some of you are working on with colorings. That this is quite relevant. So, proposition: if gamma or pi into GL into Z is a finite permutation group. And by the way, I didn't say, because I assumed maybe I should have said it. I didn't say that. Of course, when you have the chain complex, the homology is the cycles modulo the boundaries. So whenever we talk about HI, we always mean the kernel of the ith boundary operator modulo the ith plus first. These are chain complexes, and this is the usual way homologies. So in particular, the zero homology is simply C0 modulo the image of the one chains. Okay. So if we have a finite permutation rep, then the zero homology I'm doing this in the case of a knot. It generalizes. Let's keep it to knots. But this is Z to I'll call it O, where O is the number of pi prime orbits of 1 through n. What does that mean? Well, pi is a permutation representation. Elements of pi go to permutation matrices, so elements of pi act on 1 through n as permutations. Just look at the matrix and see where the permutations, think of 1 through n as E1 up to En. And see how this matrix permutes the basis vector E1 through En. That's what I mean.
Do you mean ZDs?
Pardon me?
Do you mean ZD?
No, it's a. I had to make up a letter, so I used O for orbit.
You mean with
But
the
it
V?
means
It's
Z
a knot,
is
so
one.
it's a knot.
We're
So
only
D
dealing. We're not dealing with links anymore.
No, just keep it. You can generalize this, but I don't want to subtract this. I think everything I do is going to work on this. Let's just think about this. So pi acts on 1 through n. So pi prime acts on 1 through n. You know, and just look to see what orbits 1 through n go into. I mean, well, you just just see how many you look at if some element sends 1 to 2, then 1 and 2 are going to be said to be orbit related. They're the same orbit. So I'm looking at two integers 1 through n are only in different orbits if there's no element of the commutator subgroup that takes 1 to the other. Okay.
So you're just going to partition 1 to n.
That's right.
According to where pi prime can send them.
That's exactly what I'm saying. That's right. Yeah. And you'll see why. That's the plan. And so the proof. And so of course H0 is only going to be trivial if pi prime acts transitively on 1 through n. Just everybody. The idea here is to start with a representation where AIs are in the commutator subgroup. And as I said before, if you're only interested in H1, you don't have to use a vertical representation. So the trick is to use that. And now H0 of x, v, gamma, as always, is C0 modulo the image of del 1. What's C0? Well, C0 C0 is just lambda tensor v. It's generated by E1 tensor star, En tensor star. Now, since del 1 of 1, look at this element. I'm going to be a little bit screwy. I'm going to put an x into this here. No harm. Tensor x. Since this element, and I should have explained that x is a meridian. Okay, so the augmentation of x is 1. When I take this boundary, I get t tensor v tensor star minus 1 tensor v x inverse tensor star. If you're going to mod out by all these images, in particular, you're going to start perhaps by modding out C0 by that. What's the effect going to be? It's going to be saying that when we kill this element in C0, what we're saying is that T of 1 tensor V tensor star is equal to 1 tensor V x inverse tensor star. So immediately all of this collapses down to just V. It's saying that the action of T is the same thing as simply multiplying a vector V by x inverse. And so C0 modulo the image of these chains generally, just the meridian, just that much of it. I haven't modded out by all of the image of del 1, just this chain. But this thing is isomorphic in a natural way to V, with an action that's a little bit screwy. The action Vt, meaning Vx inverse. So right away we see that this module is going to be a quotient of V. That has a serious implication. But now we have to see what happens to the other elements. So what about 1 tensor V tensor AI? What are the other generators? Well, this is 1 tensor V, the matrix AI. That's just a permutation matrix that comes from the commutator subgroup. AI is in the commutator subgroup. And so tensor star minus 1 tensor V tensor star. What does this do? When we mod out by this, killing this identifies, well, in V, think about V is just n-dimensional vectors of integers. It identifies n1 through n capital N with n pi 1 and pi n capital N. In other words, it just permutes these. It just permutes these according to according to AI. According pi according to AI. So what's going to go on when you mod out by all of these elements is you're going to take these integer vectors and you're going to identify them if some permutation corresponding to an element of the commutator subgroup takes one to the other. And that's where the orbits are coming from. In the very simplest case, capital N is 2. And you just have two vectors, n1, n2. And you've got a permutation that takes that n2, n1. Then suddenly z plus z becomes z. whole thing collapses down to the one of the consequences of all this, the corollary, is that H0 in this situation, I always get the V and the Z confused, which is why we started going to another notation. Nightmare. This thing is a quotient, or isomorphic to a quotient of V, and hence has no free submodule. Well, has no free lambda factor. So what does that mean? It means that when we take the characteristic polynomial, its module, we don't get 0. And so now let me tell you what the punchline is of everything here. These modules, HI, H0, H1, I'm just going to call them H0 and H1 instead of writing out all that stuff. These homology modules are finitely generated lambda modules, Alexander ideals, and polynomials are defined as we did for the untwisted case. Whenever you've got a module, you can look at consider a presentation matrix. Modules. We can look at delta 0 of H0. We can look at delta 0 of H1. What are these? These are the GCD of determinants of maximal size squares of matrices, of the presentation matrices. And delta 0 of H1 in the untwisted case would have been the classical Alexander polynomial. Here it's called the gamma twisted Alexander polynomial, and it's denoted by delta gamma. Also, delta H0 is not 0, since H0 has no free lambda factor. And now the surprising, maybe surprising, it's not that surprising result, which is proved which is proved in the case of fields in Livingston and Kirk and Livingston's paper, and proved more generally for unique factorization domains, the theory of UFDs in a paper of Chop, is the following result. Proposition. So I think this is Kirk Livingston, and I think one has to also say Chop in the more general case for any gamma pi to gamma n r, delta gamma divided by, I'm only calling this delta 0 of H0. I haven't given this one a name. So the zeroth characteristic polynomial of the first homology divided by the zeroth characteristic polynomial of the zeroth homology is what is a variable. We've just seen that this thing vanishes when you've got a non-abelian parabolic representation with W unit. So, as a corollary for non-abelian parabolic reps of two-bridge knots in particular, this vanishes And so this polynomial that we've been computing is the same thing. There's not a lot of difference between this and this. There's some factors. Usually the difference in W versus delta are usually cyclotomic factors. They're usually not terribly interesting for a variety of reasons. But the moral of the story is computing H1 is generally very hard. Computing H1. And of course I mean the twisted homology H1. Let me be very clear about this. It's hard. The problem is finding the cycles. It's finding the one cycles. Finding the kernel of del 1 can be very difficult. Especially if you're working over just a simple Noetherian move. You're not working over the field, this becomes murderous. And so, in many ways, it's preferable to work with Wada for a lot of reasons. But I just want to take, I know you said it just a little bit later, I'd like to take just 1 second to put together something very important that ends in red. It doesn't take much. If you want, we could take if you take a component of L1 link and you encircle it by meridian, and we call this M. Call that M. I want to think of it as an actual circle, an actual subspace of the link exterior. And we've been picking base points. Let's pick our base point right on it. Then we've got X. We've got a base point contained in the subspace of our link exterior. If we wish, we can think about the representation, gamma, restricted to this circle. What is it? The fundamental group is just Z. The fundamental group generator is identified with the whole space. It goes to the matrix. This is the arc for X0. It goes to the matrix X0. And if we do that, we can look at a chain complex. We can look at this chain complex. This is concentrated in dimensions 1 and 0. It's a very simple chain complex. It has one tensor, B tensor star for the 0 chains. And it has one tensor, let's assume that this is the arc X0. It has one tensor, a B tensor X0 for the one chain. That's all. And we can regard this as sitting inside the full chain complex in a very nice way. Whenever you've got one chain complex inside another chain complex, you can form the quotient chain complex. And the quotient chain complex, denoted usually this way, is by definition the one divided by the other. Skip the rest. The one divided by the other. And when you do that, what you get is that all the 0 chains are gone. Because this module is the same in both chain complexes. And so it's gone. And over in C1, all you've done is you've gotten rid of the X0 chain. Remember when we deleted a column in computing the numerator of Wada? We deleted a column that corresponded to X0. Okay, so over here we've got one tensor, B tensor, X1, one tensor, B tensor, Xn. And here we've got one tensor, B tensor, R1, one tensor, B tensor, Rn. Well, the homology of this complex is the relative homology, by definition. homology that you get. But if you think about how we're going to compute that homology, because we've killed C0, we don't have this problem of finding one cycles. This is the key point. We're not going to worry about one cycles because every one change is a one cycle in this relative thing. We've gotten rid of C0. That's the good part. And all we have to do is look at the co-kernel of L2. We have to look at the one change modulo of things coming in. Well, folks, this is exactly what we did when we computed water. This is the numerator. This is really, this is the model that matrix in the numerator of water represents. So, so the matrix, so this is presented by what we call M gamma. Suze and I have been calling this thing the based because you got rid of the x0 part. Base means you got rid of something. Gamma twisted Alexander polynomial. Alexander module. And we've given it a simpler name, capital A for Alexander, 0 for 0 at the top for based, gamma for the representation, looking for something that's just simple and quick. And the punchline now is that this module has a square matrix presentation. Very nice. You just take the determinant of it to get delta 0 of this module. And when you do that, this is the numerator. This is Lynn's polynomial. So this is the numerator. And so that's how all these things are all related. It's again from the point of view of dynamics and working with GLNZ representations. This module is very nice. There's a lot of things that we can see with dynamics. I believe Susan's going to talk about some of the dynamics that arises from this situation tomorrow. Yeah, I guess that's a good place to stop. Thank you.
Any questions?
Do you get more Alexander polynomials? So
Yes, that's an excellent question. Whenever you've got a finitely generated random model, you've got a whole dividing sequence of Alexander polynomials and ideals.
And you can do that just by starting with the first two and taking the factors of them.
Well, no, you got to look at the GCD of the smaller subdeterminants, and then that gives you
higher homology. The chain complex is still that big. You're not going up to homology, so you're just looking at delta K of H0 or delta K of H.
That's right. Yeah, of all those things. H0 isn't that interesting.
Oh, okay.
Generally, it's H1. One thing I would like to say, the first lecture I gave, the classical Alexander polynomial was the first delta 1, the first elementary divisor, if you remember. But we were not working with the same module. By getting rid of x0, our delta 1 became delta 0. More time to talk about this stuff. I would explain that what's going on here is in some ways very naturally viewed as going on in the universal Wheeling cover, not the universal cover. And so in the universal Wheeling cover, even the classical Alexander polynomial is the delta 0 of a homology containing the zero cover. So that's why there's a slight discrepancy there. But then there's a whole bunch of sequence of, just like you said, more. Not a lot has been done about computing hardware. I have to say, so much of this whole area is wide open, and this approach gives you lots of stuff that you can't see with combinatorics, exact sequences. I don't know any way to do excision. I don't even know if it makes sense to expect it, but the long exact sequence of a pair is very handy. It's something to do. I've always thought that you really can't do much of anything unless you have excision, so. I don't know. Is it hopeless to ask for some excision? There's a twisted quantum duality exists. And all that's defined by knowledge of the chains.
Well, thanks again.